So the first part that we did only had to do with forces and equilibrium. How much force the support gives, how much force there is inside the structure. There is another important part to what the structure does, and that is it deforms. Okay? So if I take a bar, actually, let me start with this one here first. Okay, if I take, so we're going to talk about the deformation of our bar in axial loading. So let's say that I start with a bar, and the bar in the beginning has a length L0. So that's the initial length of the bar. Okay? I go and I apply a force to the bar. So to keep things simple, I simply say that I apply an axial force to the bar, and this whole section of the bar is under constant axial load N. Okay? This is true. What I'm saying is going to be true no matter how complicated the loading inside the bar is, because it only has to do with geometry. But to simplify our idea, let's say that we have a bar. Initially, the length is L0, and then I pull on the bar. I pull on the bar, and the bar gets longer. And the length of the bar after it deforms, let's call it L. The change in length of the bar, so if I look at the deformed length of the bar minus the initial length of the bar, this thing is called the elongation of the bar. And we use the symbol delta for elongation. Okay? The elongation of the bar is delta. It's simply equal to the final length minus the initial length. So you see just from the definition that if delta is positive, the bar gets longer. And if delta is negative, the bar gets shorter. You see that the sign for delta has absolutely nothing to do with the way the x-coordinate goes. I didn't even draw the x-coordinate. Delta, which is a measure of the deformation of the bar, like the axial force, is something that tells you what the bar feels, what happens to the bar. The bar gets longer or the bar gets shorter, independently of x. So again, this one, it doesn't have any to do any, it doesn't. Again, this one doesn't have anything to do with x, okay? The deformation only has to do with if the bar becomes longer or shorter. It does not depend on x, and we can see that there must be some kind of connection. What is the connection between the elongation of the bar and the axial force in the bar? We see that the positive axial force, that is tension, somehow must be related to the fact that you have a positive elongation delta. And the negative axial force, which means compression, we can kind of expect to be related to shortening of the bar. Yes?
Was there a reason why you drew the forces as an swirly N rather than as F, FA, FT?
No, in this particular case, no. The way that I put the curly N is to simplify my life, to remind you that the convention for positive axial force is coming out. So if I define delta as the final length minus the initial length, in this picture here in which delta is positive and the bar gets longer, already kind of in the back of my mind, I see it connected to a force pulling on it. But in general, the definition of elongation is just by itself geometry. I can tell you this is a bar before it's loaded. I don't tell you anything else. I just tell you this is the bar after it's loaded. What is the elongation of the bar? The elongation of the bar is going to be L minus L0. And if this distance is b, that is going to be equal to minus b. How the bar got from here to here, maybe because I'm pushing this way and I'm pushing this way, and then maybe I'm pulling a little bit. And overall, with all this distribution of load in the bar ended up shorter. But the elongation is defined simply in terms of geometry. Okay?
Curly ends not just for inside of the system?
The curly end indicate the axial force that the bar feels. In general, So if I drew it that way, it means that maybe this is part of a bigger structure. I cut and cut. This is a bar. And where I cut here, I have an axial force N. If this complicates your life, instead of drawing it this way, you can think simply that you have the bar like this. You have the same bar at the wall like this. Instead of having an axial force F, and I can put a force here. And then I have the change in length of the bar as delta. But what I want to point out is that when I define delta, I don't even need to know what kind of loading I have on the bar. It is simply geometry. Delta positive, the bar got longer. Delta negative, the bar got shorter. We good? OK. OK, so what is the connection between the elongation and the axial loading? So we're going to talk about what is the stiffness of a bar in axial loading. So today, to simplify my life, I'm only going to think about a very simple kind of problem. I'm going to think about a problem which has a constant N, constant axial force. So a constant axial force means that I have maybe a bar that looks like that. If you look inside that bar, the axial load inside the bar at every point in the bar is equal to the magnitude of F. OK? Because any way you cut, you put any chunk in equilibrium, you're always going to find that N is equal to F. So to simplify my life, let's consider that I have a bar with a constant axial load N. I'm going to draw it like that with the understanding that what I did is I took the bar, I look at it, and inside the bar there is an axial load N, and the initial length of the bar was L0. And let's say that the cross-sectional area of the bar is A. And today, to simplify life, I'm going to say also that the A is constant. And that the bar is made of only one material. OK? We're going to do more complicated things on Thursday. But for now, let's say that I have a bar made of one material, constant axial force, constant cross-sectional area. And then I want you to think of a mental experiment. I take this bar, and I start pulling on this bar with increasing axial forces. So I pull at this level of force, and I measure how much the bar gets longer. So I pull a little bit. So this is N, how much I pull on the bar. Oh, I start pulling a little bit, and I find it gets a little longer. So I find some elongation. Then I pull a little more. Well, guess what? My elongation goes up. And if I continue pulling, I pull more, I find that it gets longer. If I continue pulling on the bar, what I find is that as long as I do not pull too hard and I deform the bar too much, the relationship between how much force I put on the bar and how much longer the bar gets for all materials up to a certain level of force and deformation, the relationship between the force that I apply and the elongation that I get is linear. And this slope of this relationship is called K, and this is called the stiffness of the bar. OK? So just from this relationship here, you say that K, you can simply obtain it at any point simply by taking the ratio of what force you have for what elongation you have. So the axial stiffness is simply defined as the ratio between, if you apply a certain axial force and you get a certain elongation, you take the ratio of the two. That is the stiffness of the bar. Now, K, this thing, is a structural property. OK? So this is a structural property. It's the properties of this particular structure, which had in a certain cross-sectional area, was made of a certain material, and had in a certain initial length. Okay? So that's the property of this structure, and it's the first time of this kind of, the first time that we look at this kind of entity in 201. Structural property, the stiffness. Okay. So of course, this is the kind of things we're interested in finding, because say that I want to know if a structure will deform too much. If I know its stiffness and I know what kind of loading is going to be applied on the structure, then if I have K, I can tell you how much is going to deform, right? So K is the kind of guy that we want to find out in 201. So how do we find out K? So before we go in that direction, let me say a few things about this somewhat simplified picture that I drew here. So the picture that I drew here is that I go up and linearly increase n, and delta keeps going up with a relationship that stays constant and linear as I increase the force. This is only true for small enough deformation in all materials, as I was saying. If you deform a material enough, normally you get a little more complicated relationships. For instance, if I take my good old slingshot here, when I start applying the force to it, in the beginning, I can keep increasing the force, and the elongation kind of goes linearly with the force. But then as I keep pulling and pulling, it gets harder and harder to do the elongation. So the relationship for rubber between how much force I get and how much elongation, how much force I put in and how much elongation I get, can be nonlinear, can be like that, right? If I can have the opposite kind of thing. Like, did you ever try to bend like a paper clip or something? You start doing it and it seems hard, and then at some point it gets easier. That's yield. The material yields to you. And if you plot the stiffness, it's not just a linear relationship. It seems stiff in the beginning, and again it gets softer. So there are material responses which are nonlinear and structural responses that are nonlinear. In 201, we will mainly focus, actually, we will only focus on structural response, which the loading and the deformation are related through a linear relationship. Not only that, but also we're only dealing with material which are elastic. Elastic does not mean linear. Elastic means that if I go up and load, I go up this way. If I come down and I unload, I come down exactly the same way. Okay, that's what elastic means. Elastic means what I put in, I get out. Okay, so in 201, we're only going to do a structural property and structural material which are linear and elastic. And this is going to simplify our life so much and make us extremely happy, because the relationships are easy to deal with. You can use all kinds of nice tools like superpositions and other things that we will use aplenty. Okay, so this is all very nice, but it doesn't give us a lot of insight about how to use this relationship. This just tells me I have this specific bar, I pull it, I get a stiffness K, and then once I measure the stiffness K, I can predict what this specific bar is going to do. But what if I want to know what a different bar is going to do, right? So say, for instance, that I take a bar, I take bar 1. Say that I take bars only made of one material. Say that I make them out of steel, because I'm extremely strong, so I can deal with steel, okay? So I take bar 1, so I take steel bar. I take bar 1, and my bar 1 has a cross-sectional area A1, and it has a length L1, okay? I go and I plot what axial force I need to get a certain elongation delta in bar 1. That's a very ugly delta. A certain elongation delta in bar 1, and I get a slope like that, and this is my stiffness for bar 1. Now I take another bar, bar 2, and the bar 2 is going to have an area A2, which is 2 times A1, and it's going to have a length same as the original length. So I'm taking a bar now, which, if this was the first bar, my bar has a bigger cross-section. It's chunkier, okay? What do you think is going to happen if I apply the same force? Say that I am here. I apply the same force to bar 1. Is the elongation going to be more or less? Less, right? Like if I'm pulling something thin, it's going to deform a lot. If I pull something chunky, it's going to be harder to get it longer. So if I do bar 1, I get a stiffness. So if I pull bar 2, I get a stiffness which is higher than the stiffness for bar 1. Now let's do bar 3. So bar 3 has area A1, but it has L3, which is equal to 2 times L1. So in the beginning, I tell you, this link shot is coming really handy today. So this was my maybe original bar 1 was this long. I pull it, and I get this elongation. I take a bar that is twice as long. I pull it with the same force. Do I get more or less elongation? More. Imagine that I pull something that's 1 centimeter long, a little elongation. Something 1 meter long, a lot of elongation, right? So how much elongation I get for a certain force has to do with how big the structure was to start with. Do you see it in your eyes? You see it in your mind. Excellent. So for bar 3, when I plot the stiffness of bar 3, I'm going to find that the stiffness for bar 3 is going to be lower than bar 1, because for the same force, I'm going to get more elongation. So this kind of tells me, I mean, this K is useful, but in terms of predicting stuff, it's not really practical. It kind of gives me an idea. It gives me the idea of normalizing things. Why don't I normalize things? So what if instead of plotting things this way, I divide the axial force N by the cross-sectional area? Why not? And why don't I divide the elongation delta by the original length of the bar? I can normalize things, right? If I do that, what I find is amazing. I find that the curve for bar 1, bar 2, and bar 3, instead of being different curves, are going to be the same line. So bar 1, bar 2, and bar 3, 1, 2, and 3, that are all made of the same material, steel, will have the exact same line. On the other hand, if now instead of just taking bars made of steel, I also consider bars made of rubber, the bars made of rubber will be like this, because I can get more elongation for the same force, rubber. And if I take bar made of diamonds, because I'm extremely rich, I'm going to get something that looks like that. So you see, this stiffness here is a property of the structure. This slope here now is not a property of the structure anymore. It's a property of the material, right? So we made a huge, huge mental step. So to do the mental step even more elegantly, let me give names to these quantities over there. So my N over A is called normal stress. And that doesn't mean that you are normally stressed, which I am. It's just that it's normal to the surface, because essentially the idea is that you have a certain cross-section A, and you have a force pulling on this cross-section N. And this force is kind of distributed along this cross-section. If you think about the stress, when you take a force and you divide it by the cross-section, kind of tells you, over how much space you have it. Like if you take a pencil and I push with the pencil with a force like that on my cheek, and I push with the same pencil but strong, with the same force but with the tip, it hurts more, right? If I push a lot, it hurts a lot. The sacrifices I do for science, right? And stress is a measure of the force per unit area. So force per unit area. In this special case, in which is one material only on the cross-section, then I can obtain the stress that we will call sigma n for normal stress. So this is a sigma, Greek letter. Normal stress, sigma n. In this case here, I can simply obtain as the axial force divided by the cross-sectional area if I'm dealing with one material only on the cross-section, because the stress will be uniform. There is no reason that a point here, a point here, a point here is going to feel something different. All the guys are the same. They all together carry the axial force n. So each of them feels a stress sigma n. This guy here is called the normal stress. And if you think in terms of units, the units are going to be Newton per meter square. And that is called a Pascal. Pascals are very small guys. And a Pascal is a very small pressure. So normally, in 201, we're also going to need with kilopascal, 10,000 Pascal, megapascal, and gigapascal. The pounds and stuff units are, instead of being Newton per meter square, are pounds per square inch. And these are called PSI, pound per square inch. 1,000 PSI is a KSI, and so on. I really am not going to use these guys much in 201. We're going to mainly use SI units for stress. So stresses, as I was saying, are very important because connected to stress is the possibility of failure. Right? Why does it hurt when I push with the pencil? Not when I push with the rubber end, but when I push with the tip. Because the nerves inside my body say, wait, it hurts, because you're creating damage. High stresses can create damage in a structure, and your nerves tell you that. So if you have a stress inside the structure, typically you may have a material property which is as sigma f, the failure stress. And that means if I push with the pencil strong enough, hard enough, so that the force divided by the tip of the pencil reaches sigma f, I'm going to make a hole in my cheek. I don't want to do that, right? So to be safe, typically you want to have sigma n to be less than sigma f. You do not want to have sigma n bigger than sigma f. And typically, if you want to prevent failure, so if you want to prevent failure, you typically want sigma n less than sigma f divided by some safety factor. Half of sigma f, a third of sigma f, right? To be safe that you don't poke your cheek with your tip of the pencil. That's very bad ideas, okay? So this is good. Stress is important. So now here, instead of simply writing n over a, I'm going to take n over a again away. Because I know that now my n over a is going to be called sigma n, stress. Now let's look at this guy here. This guy here is an elongation per initial length of the bar. Okay? So if I had a uniform bar like that, and I have an elongation delta, delta over L0 gives me what is the elongation per unit length of the bar. So delta over L0 is elongation per unit length. There is a name for this guy, and this is called epsilon axial. Axial strain. If something has a big strain, it means that for how long it was, it got a lot longer. If something has a small strain, it means it didn't change length much from what it used to be. Notice that this is in length, and this is in length. Elongation per unit length, the units for strains are meters over meters. So what that means is that strain is dimensionless. It's kind of like a percentage. How much bigger, how much longer the bar got? 3%, 1%, 7%. So for instance, I may have a strain equal to 0.01. That means that if a bar was 1 meter long, it got longer by 1 centimeter. Okay? That is our guy. Strain in percentage, no units. So on this graph here, instead of having delta over L0, get rid of this, and we put epsilon axial. Okay? Let's look at the sign conventions. The sign convention for epsilon axial go with the sign convention for delta. So a positive axial strain means that things get longer. A negative axial strain means that things get shorter. The sign for stress goes with axial force. A positive, the stress goes with n. So if the stress is positive, so a positive stress goes with tension. And a negative stress goes with compression. You see, stress and strain do not care which way the x-axis goes. Go with what the structure feels, tension or compression, and with what happens to the structure. Gets longer, gets shorter. Okay? You measure what's inside. Alrighty, so finally, we have this diagram here. And this diagram here, now all these slopes are the ratio between stress and strain. And these slopes are specific of the materials. These slopes here are called E. So this would be the E of the steel. This would be the E of the diamond. And this would be the E of the rubber. And this quantity here, E, which is defined as the ratio between the axial stress, the normal stress, and the strain that the material gets, is called the Young's modulus. And the equivalent relationship here that says that the normal stress is equal to E times epsilon axial. This is our first example of a constitutive relationship. This is our very first example of how the deformation and loading is connected at a material level. Okay? And we are done. And one last thing I want to show you is something really cool, because now if you look at this connection between here and here, you can see that, let me put it just here, a little last thing that I want to tell you before we go. You see that the way that we defined the stiffness of the structure was n over delta. If I multiply and divide by A, I get A, n over A, and here do the same thing. I divide and multiply by health, so I get L times delta over L. And so N over A, this is the normal stress. Delta over L, that is the axial strain. So that's equal to A over L times E. Kaboom! You know what is the power of that? Amazing! What this means is that if I take a bar that looks like humongous things and a certain length made of steel, and for that bar I figure out E, I can tell you what the stiffness is going to be of any other bar as long as you know the cross-section and the length. This is amazing power that we got with what? Not even an hour of work, right? So that's the kind of relationship we're going after in 201. Relationship that allow us, by knowing something about the material and about the geometry of the structure, to come to conclusion as to how the structure will behave under loading. Okay? So what we did today more or less covers what you need to do your very short first problem set. You have the support of the exercises online. I'm going to post the notes so that if it's not very clear on the board, it's going to be with nicer handwriting online. And if you have any questions or any of any sort, send emails. Actually, no, it's something totally important. Don't send emails. On the info, you will see that we are signed up on Piazza. I love Piazza. It's fantastic. You go in, you can post anonymous, you can say who you are, you write your questions. We all monitor Piazza. We answer your questions right away. You can answer each other's questions. You can answer each other's question, and it works really, really well. We tried last semester, and I think it's fantastic. I wish I had it when I was a student. Okay, so, but if you have any other kind of things, administrative point of view, sign up, whatever, email me. And we're going to try to have office hours on Wednesday, I think. Okay, I'll post it on the Stellar website. Thank you, guys. Bye. See you Thursday.